So now we are at lecture 70 and I will continue the ant colony optimization in this lecture. And today we are going to discuss something known as the meta-heuristic for the ACO. And again, I'm Dr. Ranjan Ganguly. Now, as we mentioned in a previous lecture, this whole concept of ant colony optimization was created by Dorigo, and then he and his co-workers used it for the traveling salesman problem. Now, Dorigo develops a lot of notation and mathematics for this method, and essentially he packages this as a combinatorial optimization problem. We will call it as COP. And these kind of problems are quite ubiquitous in optimization. And again, ant colony optimization is good for solving such problems such as the TSP. Now, the combinatorial optimization problem has three key parts. The first part is the search space S, which consists of a finite set of discrete design variables. So here you can note the difference between this and a typical continuous problem where you have a set of infinite number of points in the real number domain and you have essentially continuous design variables. So here you have a finite set of discrete design variable. As you have seen in the traveling salesman problem, there are only a finite number of possible paths which are possible, and theoretically you could actually find out all these possible paths through exhaustive search of the design space. But that again is computationally cumbersome in most cases. Now, beside this search space spanning discrete design variables, you also have a constraint set defining the constraints. And finally, you have the function f which needs to be minimized, as is there in typical optimization problems. So the search space S contains discrete variables with values xi. And each value xi has a value vij which is linked with it, and essentially what this means is that corresponding to any value xi, any situation xi where I is from 1 to n, there are a number of discrete possibilities, and this is essentially the set which spans the design variable. So essentially xi can take a number of values and these values are given here. Now all the feasible points which are there in this search space will satisfy the constraints, and these will be the set of feasible solutions. Now in ACO we use something known as a meta-heuristic. So before we proceed with meta-heuristics, let us define what is this complicated sounding word. A meta-heuristic is a master strategy which guides and modifies some more heuristics to produce solutions. So these solutions are beyond those obtained when searching for local minima. So it's essentially a set of rules of thumb which are created and put together at a very high level which help you to get to a global minimum point. A meta-heuristic can also be considered to be a set of concepts, and these can be used to define heuristic methods which are possible to apply to a large class of problems. So meta-heuristic tends to be very general. So meta-heuristic is very general, combines several heuristics, and hopes to find solutions to difficult problems. Now here the word hope is very important because most of these heuristic methods, they are set out using some rules of thumb inspired from biology or science, as the case may be. And the hope of the researcher is that by mimicking this kind of behavior, he or she can come up with a method which is good for solving difficult and intractable optimization problems which cannot be simply solved using the gradient-based type of methods. Now, if a problem could be easily solved by gradient-based methods, then you would not need all these heuristic strategies. Now each design variable xi, which can have all these components vji, is called a solution component. All the solution components are collected in this set C, and this is a finite set. The construction graph GCVE is drawn by putting the components in C with the set of edges E or the set of vertices V. So again, recall that when we drew the graph of the traveling salesman problem with the cities connected together, the cities essentially form the vertices and the lines joining the vertices are the edges E. So essentially that graph is completely defined by the cities V and the lines joining the cities E. So that's essentially the construction graph GCVE. Now each component Cij has a pheromone value tau ij which is linked with it. And this tau ij is a measure of how desirable that particular path is going to be. And this pheromone value is going to change as you run your program, and as time goes by, this pheromone is going to slowly diminish, mitigate, or vanish. So we can say that tau ij is equal to tau ijt, where t is time. So there is some kind of decay possible here in the pheromone value to simulate the actual ant behavior. Now ants move from vertex to vertex within the construction graph, and they are driven by information in the pheromone values to build a solution, so they prefer paths which have higher pheromone values. Now ants also deposit a certain quantity of pheromone which we call delta tau on these lines connecting the cities or the vertices which they visit. So wherever the ants have been, they have deposited a small amount of pheromone. So that essentially is a marker telling the different ants that this particular ant has been there. And remember that if a lot of time has passed, if the path is long, then this pheromone will tend to decay with that time. So more pheromone is typically deposited whenever there is a tendency to go toward a better solution. So any path which will be shorter will have more pheromone deposited on it because the decay rate in that path will be lesser. Also, different ants will use this pheromone to guide their search for a better solution. So this is how this information is communicated between the different points in the solution. So we can now define this so-called meta-heuristic. In the meta-heuristic, the first part is similar to many optimization problems, which is we set the different parameters and we start off the pheromone trails. So remember that the lines joining the cities, when they start off, we need to create some value of tau ij for all these particular lines. And that's what you set here. Once you have done that, there is a whole series of steps which we have defined in this schedule activities section, which we need to do. And when we do this, we essentially end this particular ACO Metaheuristic. Now these activities would involve construct and solutions, daemon actions, where a daemon is essentially a program which runs in the background. That is the typical Unix definition of daemon. So again, we can say there are some small actions which need to be taken here following the construction of the AND solution. And then the third step is you change the pheromone values depending on the length of the path and the number of ants who have been there and so on. So these three are the critical paths in this meta-heuristic, or the critical steps in this meta-heuristic. Now the ACO metaheuristic is a very general process for ant colony optimization. And as you can imagine, many variants are possible based on this very general definition of this metaheuristic. So like I said before, metaheuristic is essentially a very broad level guideline of a set of rules which need to be followed to solve a particularly intractable problem. So the first step is common to many optimization methods, which is essentially setting the pheromone values and starting off with the different parameters or the numerics for the problem. All the real action towards finding the solution takes place under this schedule activities construct. And the three components inside this construct are repeated until a termination criteria is met. Now, typically the termination criteria is going to be that you have to exceed a certain maximum number of steps before you terminate this algorithm. This could be something like 30 to 50 typically, and at that point you have essentially concluded your method. So today we will stop this video here. In the next lecture we are going to drill deeper into these three particular actions which we need to take in the ACO metaheuristic. See you then.